Hello. In this section we will talk about the property tables. Property tables are used in fact to extract properties for different substances. Sometimes we need to know the properties in order to perform some calculations, let's say using the first law of thermodynamics. So we need to know the internal energy or the enthalpy. In the calculation of work, maybe we need to know the pressure and the volume. So these properties are mainly given in thermodynamics in table form. In fact, a separate table is prepared for each region of interest. As we know before that let's say if we draw the TV diagram, so the TV diagram, and we draw the vapor dome, we know that we have several regions. To the left of the saturated liquid line, this region is called the compressed liquid region. So compressed liquid region. And this line here is called the saturated liquid line. So all the states that are on this line are saturated liquids. This line here to the right is called the saturated vapor line, as we said before. Saturated vapor line. And below the dome, this is a mixture liquid vapor region. To the right of the saturated vapor line, we have the superheated, also the superheated region. And also above the critical temperature, we also have the, above this line is also the superheated region. So to the right of the saturated vapor line and above the critical temperature are both called the superheated region. So for each region we have a separate thermodynamic table. So let's start with the saturated liquid and the saturated vapor line. These two lines have one table. In fact, this table is called the saturation table. Here we have the saturation temperature table, and also we have another version of this table is called the saturation pressure table. So what's the difference between the two? These two are similar. However, in the temperature table, as you can see, the first column is the temperature. So the first column is the temperature. For the saturated pressure table, the first column is the pressure, not the temperature. So now I will just give you example for the water as a pure substance. However, for other substances, the similar tables are given. So if you understand how to use the water tables, you will know how to use different tables for different substances. So table A2 and A3 are for saturated liquid and saturated vapor data. A2 is the temperature table, and since the first column in this table is the temperature, and is mainly used if the temperature is known. So if we know the temperature, we use the temperature table, and for the saturated pressure table, if we know the pressure, if the pressure is given, we use the table A3 or the pressure table. For the temperature table, so the first column is the temperature, the second column is the pressure. This is the saturation pressure at a given temperature. So this corresponds to the saturation pressure for a given temperature. So if you want to know what is the saturation pressure for a temperature of 100 degree Celsius, we will have a pressure of approximately 1 bar. We all know that under atmospheric conditions, the temperature for the water to boil, it needs to reach a temperature of 100 degrees Celsius. So this is the saturation pressure for a given temperature. Next, we have the specific volume. It is divided into two columns. The first column is the saturated liquid specific volume and is denoted by a subscript F. So F means a property that corresponds to the saturated liquid state, and G corresponds to the property of saturated vapor. So if you see here, for the saturated liquid, the specific volume Vf is multiplied by 1000. So this value is magnified and is multiplied by 1000 in order to be put in the table. So the actual value is let's say here 1.0002 times 10 to power minus 3, because this is multiplied by 1000 and is put into the table. Okay, for the internal energy also, we have UF for the saturated liquid and UG for the saturated vapor. For the enthalpy, H, so this is U, this is the specific volume, and this is H. For the saturated liquid, we have HF. For the saturated vapor, we have Hg. However, an additional column for the enthalpy is given, the HFG. So HFG is equal to Hg minus Hf. So one can say, okay, we have Hg and Hf, so all we need is just to subtract Hg minus Hf. So why we need this additional column? So what they do is they did the subtraction for us and they have put it into a new column. So because HFG is very important and is called the latent heat of vaporization. So if we want to talk about the latent heat of vaporization, HFG, so simply let's do an experiment where we have water, for example, initially is at a saturated liquid state, and heat is added until all the water is converted to saturated vapor state. So now we reach the saturated vapor state. So if we want to draw this process on a TV diagram, so this process all happen at some given pressure, and the pressure here is held constant. So initially at state 1 we have a saturated liquid and the specific volume is Vf, and heating start until all the liquid is transformed to a saturated vapor at state 2. So this is the Vg. The specific volume here corresponds to the saturated vapor specific volume and is denoted by Vg. So this line is proportional to the amount of HFG. So HFG is the energy input in order to transform 1 kilogram of a pure substance from saturated liquid state to the saturated vapor state. And this line, as you know, if we increase the pressure, as pressure increase, this line will shrink, so the HFG will decrease with increasing pressure and temperature until it is equal to 0 at the critical conditions. So we should note that HFG decrease with increasing pressure and temperature until it is equal to 0. It is equal to 0 at the critical conditions. So the energy required to convert from saturated liquid to saturated vapor will decrease when we increase the pressure and the temperature. So we can derive an expression for Q in terms of enthalpy. Since it is a constant pressure process, we apply the first law, delta U from 1 to 2, Q from 1 to 2 minus work from 1 to 2. And the work here is equal to P delta volume, since the pressure is constant and the work is integral PdV and P is constant, so it will be equal to P delta V. So as we said before, Q from 1 to 2 will be equal to delta U from 1 to 2 plus P delta volume from 1 to 2. So delta U plus P delta V is simply delta H from 1 to 2. So the heat input in this case is M H2 minus H1, and H2 corresponds to the saturated vapor state and H1 corresponds to the saturated liquid state HF. So this will be equal to HFG. So the heat input in this case is proportional to HFG, which is the latent heat of vaporization. So if we go back to the tables, the last columns are given for the property S, and this is called the entropy. We will discuss entropy later on, so now let's just leave it and focus on the other properties. If we want to practice some examples on using the saturation tables, let's first solve the following example. So we have a rigid tank, that contains saturated liquid water contains 50 kilograms of saturated liquid water, and it is at a temperature T equal to 90 degrees Celsius. So we need to calculate the volume of the tank and the pressure inside the tank. So if we draw a TV diagram, and in order to locate the state of the water here, so this is the vapor dome, and it is a saturated liquid, so it should intersect with this is the saturated liquid line, and it has a temperature of 90 degrees Celsius. So since it is a saturated liquid, the pressure heat should correspond to the saturated pressure at a temperature of 90 degree. So P here should be equal to P sat at a temperature of 90 degrees Celsius. So in order to know the saturation pressure at this temperature, since the temperature is given, we should look at the temperature table. So we go to the temperature table and we scroll down to the temperature of 90 degrees Celsius and we read the saturation pressure, which is equal to 0.7014 bars. So the pressure here is equal to 0.7014 bar. In order to calculate the total volume, so the total volume of this tank is equal to the mass into the specific volume. And since it is a saturated liquid, the specific volume is equal to V should be equal to Vf. So since F denotes the saturated liquid state. So if we go to the table A2 and we read Vf here, it is equal to 1.036 times 10 to power minus 3 meter cube per kilogram. So the total volume in this case is equal to 50 kilos times the specific volume 1.036 times 10 to power minus 3 and is equal to 0.05 approximately 2 meter cube. Another example, so let's take water inside a piston cylinder. Initially this water is a saturated liquid and has a pressure of 100 kilopascal, which is equal to 1 bar, and initially it is a saturated liquid water and it has a mass of 200 grams. So heat is added until all the water is converted to saturated vapor. Okay. So first we need to calculate the change in volume V2 minus V1. So when heating occurs, the piston will expand and will reach a volume 2 that is higher than volume 1, and so we need to calculate the change in volume, and also we need to calculate the total amount of heat input for this phase change to occur. First, if we need to calculate V2 minus V1, let's try to draw this process on a TV diagram. So this is the vapor dome. This is the pressure of 1 bar. So P is equal to 1 bar. And initially water, this is state 1, is a saturated liquid. It should have a temperature that corresponds to the saturation temperature of 1 bar. So this, at this line here, we have the saturation temperature. So since we have the pressure, we need to look at the pressure table, since the pressure is given and is equal to 1 bar. If we go to the pressure of 1 bar, the saturation temperature at 1 bar is 99.63 degrees Celsius. So this temperature during the phase change process should always be constant. So from 1 to 2 saturated vapor state. So this is at state 1, this is correspond to a specific volume Vf, and at state 2 correspond to a specific volume V2. G. So if we want to calculate the change in volume V2 minus V1, we can say it's a mass into specific volume 2 minus specific volume 1, where the specific volume at 2 is Vg and the specific volume at 1 is Vf. So V2 minus V1 is equal to the mass 0.2 kilograms times Vg minus Vf. So Vg is 1.694 minus Vf, which is equal to 1.0432. 1.0432, and we should not forget to multiply by 10 to the power minus 3. So the change in volume in this case will be equal to, if we calculate V2 minus Vf, it should be equal to 0.3386 meter cube. So for part B, if we want to calculate the Q, so Q, since here it is a constant pressure heating process, Q from 1 to 2 should be equal to the change in enthalpy, mH2 minus H1. This is already proved before. So mH2 is Hg minus H1 Hf, so m into H Fg. So 0.2 times the latent heat of vaporization. We go to the saturation table at a pressure of 1 bar and we read HFG, which is equal to 2258. 2258 kilojoule per kilogram, and so 0.2 times 2258, this is equal to 451.6 kilojoule. So 451.6 kilojoule. So that's the total amount of energy needed to convert 200 grams of water at a pressure of 1 bar from saturated liquid to saturated vapor.